Hey guys, today we're going to do two-part one, limits involving infinity. So finite limits as x approaches positive or negative infinity. The symbol for infinity does not represent a real number. We use infinity to describe the behavior of a function when the value in its domain or range outgrow all finite bounds. For example, when we say the limit of f as x approaches infinity, we mean the limit of f as x moves increasingly far to the right on the number line. When we say the limit of f as x approaches negative infinity, we mean the limit of f as x moves increasingly far to the left. The limit in each case may or may not exist. Looking at f of x is equal to 1 over x in this figure to the right, as x approaches infinity, so as we're going to the right on our x-axis, our function 1 over x is going towards 0. So we say that the limit of 1 over x as x approaches infinity is equal to 0. And as x approaches negative infinity, or we're going to the left, 1 over x is also approaching 0. So we write the limit of 1 over x as x approaches negative infinity is also equal to 0. In this point, we say that we have a horizontal asymptote of the graph at the line y is equal to 0 at the graph of f, because we will never cross 0. Horizontal asymptote is the line y is equal to b is a horizontal asymptote if the graph of a function y is equal to f of x if either the limit f of x is equal to b, the limit of f of x as x approaches infinity equals b, or the limit of f of x as x approaches negative infinity equals b. So as long as we're going towards infinity or negative infinity and we're approaching a certain number, that means we're never actually going to touch that number, and that will be our horizontal asymptote. The graph of f of x is equal to 2 plus 1 over x has a single horizontal asymptote at y is equal to 2, because the limit of 2 plus 1 over x as x approaches infinity is 2, and the limit of 2 plus 1 over x as x approaches negative infinity is also 2. Therefore, we have one or the other. In this case, we have both of them, and we have a horizontal asymptote at y equals 2. A function can have more than one horizontal asymptote, and it does not have to have any. So here in example 1, you can see that our function x divided by the square root of x squared plus 1 has more than one horizontal asymptote. It has a horizontal asymptote here, and it has a horizontal asymptote here. So we're using graphs and tables to find the limit of f of x as x approaches infinity and as x approaches negative infinity. So graphically, we can see that as we're going towards infinity, we are approaching that pink line, which is representing our horizontal asymptote. And as we are going towards negative infinity, we're approaching the pink line on the bottom, which is also representing another horizontal asymptote. Numerically, we can see as we are getting, our x values are getting larger, we are getting closer and closer, our y values are getting closer and closer to 1. And as we are getting going towards the left in our x values are closer to negative infinity, our y values are getting closer and closer to negative 1. Therefore, having our horizontal asymptotes at y is equal to 1 and y is equal to negative 1. We can use the sandwich theorem for limits as x approaches positive and negative infinity as well. So finding a limit as x approaches infinity. We have to find the limit of f of x as x approaches infinity for x is equal to the sine of x over x. So the sine of x over x. The graph and the table suggest that y is equal to 0 is our horizontal asymptote. So what do we know about this? We know, Okay, so we know that -1 is less than or equal to the sine of x, which is less than or equal to 1. So if we have the sine of x, that is bound between -1 and 1. But we want the sine of x over x. So if we divide everything by x, it is still equivalent. And therefore, by the sandwich theorem, 0 is our limit of, -1 over x as x approaches infinity is equal to 0, as well as the limit of 1 over x as x approaches infinity is equal to 0, which then tells me the limit of the sine of x over x as x approaches infinity is also 0. Oh, I was supposed to do it on that slide. Then the limits at infinity have properties similar to those of finite limits. So if L, M, and K are real numbers and the limit of f of x as x approaches positive and negative infinity is equal to L, and the limit of g of x is equal as x approaches positive and negative infinity is equal to M, then we have the sum rule where we can add both of our limits, the difference rule where we can subtract both of our limits, product rule where we multiply them. Constant multiple rule is when we multiply by a constant to our limit. The quotient rule is when we divide, but we have to make sure that the limit of g of x, or m, does not equal 0. The power rule, if r and s are integers, then we have the power of r divided by s, and the limit would then be raised to r divided by s, provided that L to the r divided by s is a real number. We're going to stop there for now, and I will see you tomorrow.